Good morning to all of you. It's fantastic to be here and tell you all about what I believe is the real next generation of accelerated technology, where it's come from, where it's going, and what it's going to do to our world, how it's going to change our world and make it even better. So Dream Beams. It's a nice, catchy title. I've actually borrowed that phrase from one of the biggest journals, physics journals in the world, Nature. Over 10 years ago now, there were 3 big papers that came out that demonstrated that this next generation accelerated technology was feasible, that it could be done experimentally. And I'm going to get, in my talk, I'll give you a little bit of a backstep of where that thinking came from. Because anything that's to do with next generation technology, if you're a scientist, an inventor, an engineer, a technologist, the basis behind everything that you do is imagination. Because I really believe that imagination is more important than knowledge. Imagination is where ideas come from. When you have these crazy thought experiments, you think something up that nobody's thought of before. Those new ideas, that is the basis for all science and discovery. That is where it all comes from at the end of the day. And science is the practice of testing out those ideas. You apply critical thinking, you test your idea, you think about, is this hypothesis going to work? And you can test it out through mathematics, or you can test it out through experiments and engineering. But I am not alone in thinking this. This is actually a quote that comes from one of the greatest physicists of all time, Albert Einstein. So a lot of his work came from his imagination, from his thinking, long time thinking about the world around him and how the world works. And his imagination is what's given us modern-day physics and modern-day technology as we know it. All the papers that I could pick, and there are many from the early 1900s where he tested his imagination through mathematics, the one that I would like to show you is his paper from 101 years ago, in which he had the idea that atoms, particles of light could be combined. The idea that packets of light, called photons, could be given out by energized atoms. And further to that, he had the idea that the way that those energized bits of matter give off their energy in light can be via spontaneous, which kind of random emission, or stimulated emission of radiation. That SER is the SER in laser. So his idea back in 1917 was the basic concept of the laser. And it took a few decades later for someone to realize his dream, his imagination, and build the first laser. So Einstein in those days, he didn't have the equipment to build this for life. He tested his imagination using maths and equations. He tested it out on paper, and he justified his imagination, and that is what this paper represents. Now, lasers have come a long way since then, since the first one was built, and now they are in the background of everyday technology through really kind of hard-hitting technology that touches on the internet, for example. That's how we get fast data passing around the world is in bursts of light traveling through fiber optics. It can cut through steel. It can measure the distance from the Earth to the moon. It can be used to detect gravitational waves. But it's also been applied in sectors that we know more about. So in terms of cosmetics or medicine, laser light shows, all sorts. So it hits on into entertainment, in science, technology, medicine. And so it's, has come a long way since 101 years ago when Einstein wrote those basic ideas down on paper. So taking this idea of having a thought experiment, testing it out, building it, and then improving it. So that's what people are still building lasers now, and they're making them better, they're making them faster, stronger, smaller, all of these things. That kind of process is where technology evolves, where new ideas and new technology comes from, is someone saying, how can I make this better? How can I make this better, and how can I use that to improve the world? That idea is the basis behind computing. So back in 1956, this was a 5-megabyte hard drive from IBM. You can see there's quite a few people shoving that onto a lorry there. 5-megabyte hard drive is, a couple of photos these days, song file or something. But computers, way back in those days, were actually built for science. They were there to do the mathematical equations that could calculate trajectories so that we could put people in rockets and send them to the moon. That's what computers were originally there to do all the great equations and mathematics to work out the world around us. But people started thinking about how can I make computers better, faster, stronger? And now computing literally runs the world. It's how our world runs. It's on the fact that computing and memory and hard drives have got smaller and faster, so that these days I can Skype my sister in Sydney while Insta-storying me arriving at the Harwell campus yesterday morning, and take a snapshot of me doing that at the same time, because I can walk around with a dual-core processor in my handbag, and I'm sure all of you have got one of those as well. So computing has come a long way because we've made it smaller, better, and faster and stronger. That idea is what we want to apply for accelerators. Accelerators have been around for decades. This is a picture of the Large Hadron Collider, the big CERN facility in Europe. And these systems, accelerators, were originally built to do science. Because if you accelerate particles to almost the speed of light, you can probe matter and you can probe the universe and what's going on around us. And these machines have been used for a very long time now, and they've been doing very, very, very well at what they do. But they're also used not just for discovering where the world came from and discovering things about materials and processes of life. They're used an awful lot in industrial sectors that touch upon our lives, because these beams of particles or the beams of X-rays that come from these accelerators can be used for imaging, inspection, and treatment even. We've just heard now how they can be used for medical treatment and cancer treatment. So they touch upon all different areas. People use them to inspect parts of planes. People use them to inspect through large things that are coming through cargo that's coming across our borders. People are using them to test and explore new materials, carbon fiber-based composite materials, advanced materials. They're used for testing energy storage, and when people are building new batteries, they want to see inside these batteries and want to see how these things are working and how you can make them better. And they're also used an awful lot in big industries like the nuclear and oil and gas industries, where you want to inspect very large things. And in order to do that, you have to send a very hard and very fast energy, a beam of light or particles through it. So really, all of these things matter to us. They're all part of our life, and they all affect us. And at the basis behind that imaging, inspection, and treatment is a particle accelerator. So we've got accelerators already. Why would we need any more? Well, being a physicist and engineer, we can't help ourselves. We always want to make things better. We want to make things better, faster, and stronger. And in the 70s, there were a couple of physicists that thought, how can we make really great accelerators? Now, the basis behind any accelerator is this key equation here, which some of you at school should be learning and knowing a lot about right now. F equals ma, force equals mass times acceleration. If you have a particle with mass and you want to accelerate it, speed it up to a high speed, you need to apply a force. Now, the force that is in action in an accelerator is an electric field. So does this mean anything to anyone right now? This funny left-hand figure? There's a few. I can see a few. That rule there for the Lorentz force, which some of you will learn if you're doing up to A-level physics, tells you that if you have a charged particle, a particle with a charge, whether it's positive or negative, if that charged particle sits in an electric field, it will experience a force. And if you get those things aligned properly, you can make that force go forward. That is the basis behind any particle accelerator. An electric field is pushing or pulling on charged particles. In order to make your particle accelerator stronger and faster, there are a couple of things that you can do. One, you can make your electric field extend very far, and you can have lots of little different cavities, so that as the particle goes through, it's going pushed and pushed and pushed and pushed, or pulled, either a force, and you can make that thing very, very long and make your beam of particles travel very, very fast. that is the basis of particle accelerators that exist right now. That's one of the reasons why CERN is so large, because of the huge speeds, the huge velocities that we want to get to in order to explore the fundamental beginnings of the universe. You need extremely high particles, and they've done that putting accelerators back to back. And each cavity, each part of that, is trying to get as strong as it can. So the other thing that you can do to make your particle accelerator stronger and faster is make your electric field very, very strong, so that each push, each pull that particle feels is faster, it's stronger, so your acceleration is higher. So you either make this thing longer, or you take the innovative step, which is to make the electric field stronger. And so people were saying, okay, well, that's let's go down that route, but how are we going to do that? How are we going to get an extremely high electric field? And one of the thought experiments, the ideas that people came up with, was kind of inspired by the acceleration that a wake surfer can feel when they're zipping behind a boat. So a boat traveling through a lake or the sea, behind it will set up these really strong waves. And if our particle is the surfer here, that surfer can gain speed by simply kind of riding those waves. And if you get that really right, you can get to really high speeds and do some cute little tricks like this. But that thought experiment was the basis, way back in the 70s, of a new era of accelerator technology, where we actually make the electric field really, really strong. Now, that boat traveling through the lake is actually the action of a laser traveling through matter. But when people started doing the equations and started figuring this out in a little bit more detail, they realized that the light beam that they would need, that would have to create a wave in matter itself, would have to be pretty extreme. Enter lasers, because lasers are extreme beams of light. And inside those extreme beams of light are electric and magnetic fields. It's part of the electromagnetic spectrum. And it's the electric field inside that laser which is going to give us our pushing force and drive our surfing wake so that our particles can gain speed. So we need pretty much the most intense lasers in the world, which when I tend to describe that and I say I work with the most powerful lasers in the world, people get all these kind of ideas in their head, which in a way, the only part of this which is actually realistic is this focusing part of it here, the parabolic focusing. That's actually what we use on a much smaller scale to focus our lasers down to an extremely high intensity. So the beam of light is extremely intense and the electric fields are boosted. Now, what happens in real life, these lasers have been around for a few decades now themselves, and they really are quite punchy little things. I've got a little video here to show you. There's going to be a siren and a bang, so just hold on to your seats. But this is one of the lasers that we have down at the Rutherford Appleton Laboratory. It's called the Gemini laser. And every single time we press fire on that system, it sends a packet of light that we call a laser beam. It's a very short beam of light. So not like this laser here. When I press fire on this laser, it sends a beam of light. When we press fire on these lasers, a single bullet of light comes out. And because it's short in time, and we've packed that energy in a short amount of time, the power is high. Because power is how fast you deliver energy. And we can deliver that energy very fast. In fact, we deliver these beams of light in under around a trillionth of a second. So that's how you get to extraordinarily high powers. So that's, oh, there's a one missing there. One with lots of zeros. One with 15 zeros after it. It's what you call petawatt. It's extremely high power. But that's not where it ends, because lasers are light. And light can be focused in space just by using lenses and mirrors like you do in school already with focusing light down. We can also focus our lasers down. And that's how we get to extraordinarily high intensity, because intensity is a measure of how fast you deliver that energy and over how tiny a spot. Now, this tiny little spot that we focus our lasers is about a 20th the width of human hair. So each strand of hair, you divide that by 20, and that's about how tiny our laser spots are. And because of that, we get to extraordinarily high intensities. Now, the intensity of the sun, which is a good time of year for me to talk about this, that we feel when you're out, even closer to the equator than we are now, is about 0.1 watts per centimetre squared. Whereas the intensity of the laser beams that we need to do this new era of acceleration is 1,000 billion times more intense. A huge number. But that's about the right number that we need to do this extreme acceleration. So what happens when you use these lasers and you shoot them at stuff? Well, you get a very beautiful expulsion of color and light that we can capture with a camera. But if we were to use things that are looking at other than the visible light that's coming off, if we look at the particles and the X-rays that are coming off, we know that we've entered a new paradigm in acceleration. This thing that we make is called a plasma. It's simply the fourth state, beyond the solids, liquids, and gases that we use all the time and we're pretty familiar with. We live amongst these three phases of matter on Earth. But there's actually a fourth way that the atoms containing a positive center surrounded by a cloud of electrons, there's a fourth way that can be arranged, and that's in the plasma state, where you rip apart, you free those electrons from the center. So no longer have you got this atomic structure anymore, you've got this bubble of charged particles. The laser is strong enough and intense enough to create that plasma, so that's step one. But now we've got an electric field from our super intense laser in the vicinity, in the local area of charged particles. So that laser streams through, and behind it, in that plasma medium we've formed, it forms waves, just like the boat going through the lake forming waves behind it. And now we've set up a situation where the electrons can surf and ride those waves to be boosted forward with a very, very high energy. So these little dots here are the electrons, and they're being propelled, pushed forward simply by the huge electric field in those waves that we've formed. This is a simulation. This is a real simulation using equations that predict what happens when light goes through this plasma. And it comes from the left, goes across to the right, and it's kind of sitting at the front here. So we're actually traveling in a frame that follows the laser itself. And I'll just go back again to play that. And as it streams through, it pushes some of the electrons out of the way, and they go up and over the back, and then they're propelled here. This little beamlet here is electrons that are being pushed and accelerated up to the speed of light. But they're also doing an extra little cute thing, which is they're going forward, but this little bit here was vibrating up and down, so they were wiggling. Now, electrons, particles that go forward and wiggle at the same time, also give off bursts of X-rays. So this system here not only gives us a really nice beam of high-energy particles, there's also a burst of X-rays that come out. Now, this system has been developed by groups from all over the world, all the different big continents. There's lots of different groups and physicists really excited by this idea, and they're building these for real. So we've been doing this for quite a few years now, showing that we can use a laser, focus it into a little puff of gas, and then out of that comes an extremely high electric field, electron beam. And because we've set up an extreme electric field in this little capillary. Now this, just for size, would fit in the palm of my hand. It's a very small little device. And just to put that into perspective, at the Rutherford Appleton Laboratory where I work, which is down in Oxfordshire, at the top here is the UK's synchrotron light source. And in the centre, underneath the ground here, is an accelerator that's boosting the electrons up to a speed of 3 GeV, which is, let's just say, is very large speed. But we're doing pretty much the same kind of thing in a building. I'm going to hold this, my hand's shaking. In a building here, in a tiny target chamber, using something that fits in the palm of my hand. So taking the idea of making the electron accelerator 10,000 times stronger means that that little accelerator becomes also 10,000 times smaller. So this idea is getting really exciting. Is this where the next generation of accelerator is going to come from? That's what we're working on. Now, going back to my reasons for doing that, there are reasons for doing that for science. We want to build the next generation of Large Hadron Collider. Where's that going to come from? Are we going to build a bigger one that gets these even bigger than CERN? Or are we going to use our idea of using stronger accelerators to build a system which is smaller but does just as well? Or we can use this for innovation in other areas. And I'll just give you a few examples now where we're demonstrating that these accelerators are not only great for the future of exploration and science, but also for the future of these really impactful industries. Do you remember those X-rays I spoke about? The little X-rays that came from the electrons wiggling as well as being pushed forward? Well, they have extraordinary high-resolution imaging power, so that we can take things like this, which are pieces of human bone or small biological samples, and take very, very high-resolution 3D images. This is the kind of quality of imaging that you only really get using that large synchrotron that I spoke about, or a machine that would fit on this stage, but it would take a few hours to make an image of this quality. With our laser accelerators, we can get this quality in a few minutes with a system that could easily be squeezed into this room and hopefully on this stage in a few years' time. We've also been applying this for next generation materials, composite materials that will end up on planes and other big materials here. So what we're able to do is see in absolute fine detail these carbon fiber structures, these little dots here. That's not fuzziness on the projector. Those are real little dust fiber particles in composite materials. We can see this with very, very high resolution. So people who are making the next generation of materials, they can see what happens to their material, they can test it, and they can see how strong that is and how it'll be affected if you do things like deliberately damage it, deliberately try and squash that material. And applying this again for planes, but also for nuclear inspection, we can make our laser accelerators generate bursts of X-rays that are very, very high energy. So high energy that they can get through jet engines, they can also get through nuclear waste barrels, so that we can see inside jet engine blades, and we can see and can check those blades for cracks and damage. Or we can see inside nuclear waste barrels in order to create 3D images of what's going on inside, so that you can build up an idea of what these things look like and make sure that they are contained properly. And finally, this is a really neat idea that I really like, which is taking old ideas, the idea of radar or sonar, which is where you send out a burst of energy and you look at the reflections coming back. And the time at which those reflections come back can tell you what it reflected off. So you can build up a picture of depth. And the idea here is using a laser accelerator to generate a burst of electrons that come streaming out through one barrier. They reflect off with some X-rays. The X-ray reflection comes back. You detect it. But they go through another object, and another burst of X-rays comes back. And you can build up this picture so that you can build what we call a depth profile, so that you can see through barriers, so that you can see through walls. And this particular inspection here for defense and security is being able to see landmines below the surface, so being able to burrow through the ground and check for things ahead of you. So I'll wrap up now, but this idea of thought experiments, of imagination, and then applying that, testing that, and thinking about how we can make the world better with those ideas is the basis behind everything that we do in the laser accelerator community, the global community of laser accelerators. We take that research and we think about, well, how can we use that research to make something better? So we're innovative. And then once we've thought about how can we make something better, we then think, what do we need? What else do we need to discover to make this a reality, to build this in real life? So this cycle of research into innovation and innovation into research, it's what drives us all, really. So I'll just wrap myself up now, but if everything I've just told you is leaving you feeling a little bit like this, then don't worry. In fact, I would say welcome to science, because every day scientists, engineers get this little fuzzy feeling of, oh, not quite sure I understand that, or you simply get a wow moment. And it's that kind of experience which is behind everything that we do in science and research. A lot of scientists, they're driven by wanting to know more. There are scientists who are driven to want to make the world a better place. But every day when we make steps going forward, pushing the knowledge frontier, making new ideas, inventing, imagining the future, this is what we're doing to try and make the world a better place. And we believe with laser accelerators, we can really do a lot of things to make the world a better place and to discover even more about the universe. So imagination, I really do believe, is more important than knowledge. Imagination comes first. Then we do need a bit of knowledge. So if you do have an idea, if you're excited about this, there are a few steps you need to do to become someone working in this. So you do have to do a bit of background, you have to do your science degrees and get involved in research. But knowledge comes after that original idea and that imagination. And in the UK, there are lots of different groups, there's lots of different activity, lots of different universities and institutions involved in this. So if you've got excited about this and you think, yeah, I really want to be a part of this, I want to help and be a part of the team that's going to realize these incredible dream beams, then there are plenty of people in the audience today, experts from all over these different universities that you can come and speak to and find out more about how you can get involved. So thank you for listening. I'm available on all different social media channels if you want to kind of find out a bit more about what my job is and what I do in physics and laser accelerators. And with that, I will finish up, and I wish you a very happy day as part of this Eupraxia Symposium.